Hello, this is topic 7.10 for AP Chemistry, reaction quotient and the Chatelier's principle. Today's objective, be able to explain the relationships between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium. In 7.3, we looked at the reaction quotient Q, and it's used for systems that are not at equilibrium. This feels like a long time ago, actually, not gonna lie. While the equilibrium expression, capital K, is used for systems that are at equilibrium. So when a system is stressed, it causes a reaction to be out of equilibrium, and then the reaction will have to respond to return back to the equilibrium. So for this topic, we are comparing Q and K, and that's something you need to kind of wrap your head around in order to get this topic down. If Q is equal to K, that means we are at equilibrium. If Q is less than K, so I'm going to just kind of jot this down. Well, Q is equal to K. If Q is less than K, that means K is greater. The ratio of the products to reactants needs to increase. Therefore, the reaction will proceed to the forward direction to turn the Q into K to make them equal. If Q is greater than K, the reaction will proceed in the reverse direction to have more reactants, essentially. Changes to the concentration or partial pressure change the value of K, but not the Q, but not the value of K. Changing the temperature will change both Q and K. So remember, like before, the only thing that will change a equilibrium expression, the K, is the temperature itself. Changing concentrations only affect the value of Q. Changing the temperature affects both, but you need to change the temperature in order to affect the K. So we're looking at this system. A plus B plus 3B produces C plus 2D. There is your Kc sub C, 3.5 times 10 to the negative 4. Initial concentration is 1 for all reactants and products. You solve for your Kc expression, which you should know how to do already, set that equal to the Kc value. Then you plug in your number. Okay, so then whatever that expression is, you plug in your initial values, your initial concentrations or partial pressures, and then you end up with getting the Q because this is not at equilibrium. So you do the initial ones. Compare Q and C. Since 1 is technically greater than 3.5 times 10 to the negative 4, that means Q is greater than K. The reaction will need to go to the reactants to decrease the Q. So you look at how the change is set up in the ICE table here, because we're going from products to reactants because the Q is greater. Notice the switch. So the products are decreasing by some value of X depending on the stoich for the coefficient in the front. And then by adding it to the reactants, you're shifting it towards equilibrium because of the Q being greater than K. Then you can solve using your calculator, etc. So let's consider the following reaction. We have I2 plus Cl2 producing ICl. The reaction is this at 25 degrees Celsius. We have a Kp 81.9. Reaction mixture at 25 degrees Celsius contains 0.10 atmosphere, 0.100, and 0.100 atmosphere. Find the equilibrium partial pressures of I2, Cl2, and ICl at this temperature. So for this, we are going to consider the Chatelier's principle. So how do we do this? So first we got to figure out what is my K sub C, what is that expression, and then, or Kp because it's pressures. Anyway, so K sub P equals P ICl squared over I2 times Cl2. Not that bad. So for now, what we need to do is set this. So this is going to. So to find the Q now, we have the expression set up. We got to set this. Use that expression to solve for the reaction quotient to see which is greater, the Q or the P. So I'm going to plug in my values from my problem. 0.100 squared over 0.100 times 0.100, and that equals 1, right? So my Q is less than K. So that means my reaction will need to go to the products. So I'm going to fill in my my ice graph, my ice table, whatever you want to say. So P sub I2, ooh, that's ugly, can you see that? P sub I2, P sub Cl2, P sub ICl. So my initials are all 0.100 atmospheres. So we said that because my Q is less than my K, I'm going to proceed towards the products. So that means I'm going to have to form product. So to do that, you have to take away from the reactants and give to the product. So stoichiometrically, P sub I2 decreases by minus X, so it is PCl2. But because ICl is increasing and there's a 2 for the coefficient, it's going to increase by 2x. At equilibrium, I have 0.100 minus x, 0.100 minus x, and 0.100 plus 2x. So I'm going to move over to the next slide, and then we'll see what we have. So I'm going to just move over to I just kind of cleaned up the table, so then now, or the slide, so P sub I2, P sub Cl2, P sub ICl. So what I'm going to do now is I'm going to solve for my K, my expression, my equilibrium expression. I'm going to solve for that with what I have at equilibrium and then set it equal to 81.9. So K equals, so using from before, so it's 0.100 plus 2x squared over 0.100 minus x times 0.100 minus x, set that equal to 81.9. So you can either solve it with your graphing calculator, with the problem solver function, or because of the way this is kind of written out, you can kind of just solve for x. So what I mean is, if you were to do it this way, so k equals 0.100 plus 2x squared over 0.100 minus x squared. Luckily this works out, and that's equal to 81.9. Take the square root of both. Math-wise, you will end up with x equals 0.0729 for my x. So in the end, what are my final answers for these at equilibrium? So P sub I2 equals 0.1 minus 0.0729, so 0.027 ATM. P sub Cl2 will be 0.027 ATM, and then P sub ICl 0.246 ATM. So since I'm running out of space, I didn't show the work, but just to be thorough, and remember that when you're doing this stuff, you probably need to show your work. So I'm going to erase this up a bit. So you probably should have done this for a thing. So P sub I2 equals something like that. And do that repeatedly for the other two pressures. So these answers do make sense because the reactant pressures have to decrease, which they do, to form more product, so the product pressure should increase. You have a reaction here. The K sub C equals to 128. The initial value is provided in the table. Calculate the value of Q to determine the direction the reaction will go to reach equilibrium, and then find the equilibrium concentrations. So Q sub C equals, so this is concentration, so concentration B squared times concentration of C over concentration of A. So I'm going to plug in my initial ones to see how it fits with the K. So 3.20 squared times 1.85 divided by concentration 2.50. So I will end up with 7.58. So just so we're clear, my KC expression was B squared times C over concentration of A, and that's equal to 128. So if we see here that my QC is less than my KC, therefore it has to proceed to products to make the Q bigger. So they may want to explain this, like in words. So Q sub C is greater than K, sorry, Q sub C is less than K sub C, therefore it proceeds to products to make Q bigger. Q sub C is less than K sub C, therefore it proceeds to products to make Q bigger. Okay, not too bad. Okay, so now that we have our Q sub C, gotta use my K expression, get to equilibrium, and then plug in my numbers, etc. Okay, very good. So how much does this change by, and what's at equilibrium with X, and without X means when you solve the problem. So according to this, my A will decrease by X to make products now. So plus 2X for my B, plus X for my C. So 2.50 minus X, 3.20 plus 2X, and then 1.85 plus X for my C. So I'm going to take my K sub C and that expression, plug in my numbers, and set it equal to 128. So 128 equals, yeah, so 3.20 plus 2x squared times 1.8 plus x over 2.50 minus x, sorry, for my A. And you got to solve for x. So hopefully you have the numeric solver for your calculator, and from there you can figure out what the answer is. So when I do this, my x actually equals 1.4968, blah, blah. So looking at how my sig figs up here, I only have 3 sig figs. So this should be 1.50. So 2.50 minus x, 2.50 minus 1.50 is 1.00 molar. 3.20 plus 2 times 1.50 will give me 6.20 molar. 1.85 plus 1.50, 3.35 molar. All right, very good. So if you have any questions, please let me know. Thanks.